The study of aerodynamics begins with the understanding of the four forces of flight. While an airplane is in flight, there are four forces acting upon it. They are lift, weight, thrust, and drag. Lift is the upward force created by the wings as air flows around them and keeps the airplane in the air. Weight is the downward force toward the center of the earth, opposite lift, which exists due to gravity. Next, we have thrust. This is the forward force generally created by the aircraft's propellers or turbine engines, which pulls or pushes the aircraft through the air. Finally, there is drag. Drag is the force acting in the direction opposite of thrust, which fundamentally limits the performance of the airplane. When an aircraft is maintaining its heading, altitude, and airspeed, it is said to be in straight and level, unaccelerated flight. In unaccelerated flight, lift equals weight and thrust equals drag. Let's look at these four forces in a little more detail. The key to an aircraft being able to fly is lift. Looking at a cross-section of a wing, we can better understand how the lift gets generated. A wing is a type of airfoil. Airfoils in general are just any surface that generates an aerodynamic force as a fluid. In our case, air moves around it. Don't confuse a fluid with a liquid. Fluids are any substance that deform under an applied stress. Liquids, gases, and plasmas are all considered fluids. In addition to the wings, all of the flight control surfaces, as well as the propeller, are considered airfoils. The aircraft's fuselage is even an airfoil, but it's not very good at producing lift. Before we get too in-depth, let's introduce a few new terms. The forwardmost portion of the wing is called the leading edge. The aftmost point is called the trailing edge. If we connect these two edges together with an imaginary line, this line is called the chord line. As an airplane flies through the air, the path that airplane travels along is known as its flight path. The airflow that flows around the airplane as it travels through the air is known as the relative wind. The relative wind is parallel to, but opposite, the aircraft's flight path. The angle between the chord line and the aircraft's relative wind is called the aircraft's angle of attack. The angle of attack is a major factor as to how much lift the wings generate. So now that we've got those terms out of the way, how does a wing actually create lift? Well, there are two major theories working in unison that explain the creation of lift. These are Newton's three laws of motion and Bernoulli's principle. While all three laws of motion apply to flight, the third law has the most significance to lift production. Newton's third law states that for every action, there is an equal and opposite reaction. If you stick your hand out of a moving car's window with your palm flat and thumb forward, and then rotate your hand thumb side up, you will notice that your hand will want to lift up. By rotating your hand, you are deflecting the air that comes in contact with your hand downward, and as a result, the air will push your hand up. This is similar to how a wing works. In normal flight, as air flows around the wing, the air gets deflected downward as it flows smoothly around it, and as a result, the wind will lift the wing up. The other main theory of lift is Bernoulli's principle. This principle states, as the velocity of a fluid, in this case air, increases, its internal pressure decreases. We can visualize this by having air flow through a tube with a narrower middle section, which we will call a venturi. As air enters the tube, it is traveling at a known velocity and pressure. When it arrives at the narrower portion, the velocity increases to allow all of the air through. As the air's velocity increases, the air's pressure decreases. Then, as the air exits the narrower portion, it returns back to its original velocity and pressure. Now, let's flatten the top part of the tube. Granted, the effect will not be as pronounced, but there will still be a change in velocity and pressure as the air moves through. Now, how does this relate to a wing? Well, if we replace the bottom protrusion of the tube with a wing, in essence, we have the same thing as the venturi. As the air passes over the wing, each layer of air gets deflected less and less, until finally we reach a layer where the air is not disturbed at all from the wing. This can be thought of as the top of the venturi. An airplane's wing is shaped similar to that of a venturi. The top is rounded, while the bottom is relatively flat. Because of this, the air traveling over the wing will increase in speed, and as a result, will have a lower pressure than the air below the wing. This imbalance in pressure is called a pressure gradient. Wings are designed to create this kind of pressure gradient because air always moves from areas of high pressure to areas of low pressure. Since the wing is stuck in between these two areas of unequal pressure, it is lifted towards the area of low pressure by the force of the higher pressure air trying to move to the low pressure side of the wing. Now that we've covered the two theories behind lift, let's discuss all the factors that determine how much lift is produced. The best way to discuss this is through the lift equation. Don't worry though, this isn't a math lesson. Lift equals 1/2 times the air density times the surface area of the wing times the airplane's velocity squared times the coefficient of lift. For the most part, this should be fairly straightforward. The only one that might confuse you is the coefficient of lift. The coefficient of lift is simply just a number that is associated with a particular shape of an airfoil, as well as that airfoil's angle of attack. Generally speaking, there are only two ways a pilot can control the amount of lift the wings can generate: airspeed and angle of attack. The faster the airplane travels, the more lift the wings will generate. Similarly, the higher the airplane's angle of attack, the more lift the wings will generate. However, there's a limit to this angle. Let's look at this using a chart. This chart is plotting the coefficient of lift of a particular wing as its angle of attack increases. Lift will continue to increase until a certain angle of attack, called the critical angle of attack. After this point, the wings still create lift, but the amount of lift created is decreased. This is called a stall. When some people think of the word stall, they think about the engine stalling. However, we are talking about an aerodynamic stall, which has nothing to do with the engine. Stalls happen when the normally smooth airflow over the wing separates from the wing's upper surface, resulting in a turbulent airflow. The parts of the wing that have turbulent airflow passing around them are not producing any lift. For a given airplane, a stall will always occur at the same angle of attack, the critical angle of attack, regardless of its airspeed, attitude, or weight. Here's a wing at normal cruise angle of attack, something small like 4 or 5 degrees. Increasing the angle of attack will progressively cause more and more disruption of the airflow on the upper surface of the wing. Early on, the airflow will separate at the trailing edge. As the angle of attack increases, the separation of the airflow moves from the trailing edge of the wing to the leading edge. As this separation occurs, the airflow will become more and more turbulent, and less lift gets generated. Different airplanes will exhibit different stall characteristics, but generally coincide with mushy, sluggish flight control responses, a stall warning horn, a buffeting or shaking feeling of the airplane and pilot's controls, and once the stall occurs, the aircraft's nose will pitch down and the aircraft will begin losing altitude. Since the stall is a result of an excessive angle of attack, the only way to recover from a stall is to reduce the angle of attack below the critical angle. Power should be added to minimize the amount of altitude lost in the recovery and increase the airplane's speed as quickly as possible. In addition to the aircraft's airspeed and angle of attack, there are other factors that affect the amount of lift created by the wings. However, the pilot does not have control over these factors. These factors have to do with the design of the wing itself and consist of the wing's planform, camber, aspect ratio, and wing area. The wing's planform refers to the shape of the wing when viewed from above. The elliptical wing is ideal for flight at slow speeds, but does not have favorable stall characteristics. They are also very expensive to build. The rectangular wing is less efficient than the elliptical, but has better stall characteristics. Tapered wings result in less drag and more lift, especially at high speeds. Low-speed aircraft like the Cessna 172 will use a combination of rectangular and tapered to get the best of both. Swept-back and delta wings are most efficient at high speeds. The camber is the curvature of the wing. A wing with zero camber would be considered symmetrical about the chord line. Camber is usually designated into an airfoil to increase the maximum coefficient of lift and thereby minimize the stall speed of the aircraft. The wing's aspect ratio is the relationship between the length and width of the wing. Generally, the higher the aspect ratio, the more efficient the generation of lift is. For example, gliders have very long, skinny wings, giving them a higher aspect ratio compared to a Cessna 172. Finally, there is the wing area, which is simply the total surface area of the wings. The larger the wing area, the more lift the wing can produce. Looking back at the lift equation, we can see that the wing area is incorporated into the equation. The rest of the wing shape factors are merged into the coefficient of lift variable. We saw how pilots can control the lift generated by the wings changing the aircraft's speed and angle of attack. However, most airplanes come equipped with one or more additional ways for the pilot to manipulate the wings, and in essence, change the shape of the wings. These are called high-lift devices, the most common of which are trailing edge flaps, or just flaps for short. High-lift devices such as flaps are designed to increase the lift and drag generated by the wings at low air speeds. Flaps are particularly important for the approach and landing phases of flight. Use of flaps during a landing allows the pilot to fly at a fairly steep descent angle without gaining airspeed, and allows the airplane to touch down at a much slower airspeed. There are 4 popular types of flaps, each with their own set of characteristics that designers use to best suit their airplane. The plane flap is attached to the wing by a hinge at the front of the flap. When deflected downward, it changes the chord line and increases the camber, which increases the wing's ability to create lift. The split flap is hinged on the bottom of the wing. When deployed, it looks like the wing splits, which is where the split flap gets its name. This leaves the top edge of the wing unaffected and significantly increases the amount of drag created compared to the plane flap. Next is the slotted flap. This acts similarly to the plane flap, but when extended, the flap slides slightly backward, creating an opening or slot between the two surfaces. This slot allows the air below the wing to flow through the slot and onto the top side of the flap. This airflow energizes the air on the top of the flap and delays the air from separating away from the wing, which will allow the wing to generate more lift. Finally, there are Fowler flaps. Fowler flaps ride along a track and slide outward from the back of the wing before rotating down. When extended, they increase the size and surface area of the wing, which, if you remember from the lift equation, will increase the total amount of lift created by the wing. This type of flap is often found on larger jets, and on some aircraft, there can even be slotted Fowler flaps, which allow the airplane to use the advantages of both a slotted flap and a Fowler flap when creating lift. Flaps can generally be lowered in steps, or more precisely, in set degree amounts. Initially, the input of flaps will increase lift by a larger amount, with only a small increase in drag. As the flaps are extended further, usually around the halfway point, lift increases only slightly, and the amount of drag created increases rapidly. Now that we have an idea on how lift is generated, let's discuss the 3 remaining forces, starting with weight. Weight is the force of gravity, pulling the aircraft back down to the ground. This force always acts vertically downward to the center of the Earth, no matter what the aircraft's attitude. The weight force always extends and pivots from the center of gravity, also known as its CG. Keep in mind that the weight of an aircraft is not constant. It will vary with the equipment that is installed, as well as the passengers, cargo, and fuel. Throughout the flight, the weight will be slowly decreasing as fuel is burned to power the engine. Next is thrust. Thrust is the forward-acting force, opposing drag, which propels the airplane through the air. In most general aviation airplanes, thrust is generated from the propeller. Larger jets get their thrust from their turbine engines. Similar to lift, thrust is generated from the same principles as lift, but in a horizontal direction. A propeller is an airfoil. As such, it rotates, and its blades accelerate the surrounding air towards the aft end of the aircraft. And, as illustrated with Newton's third law, the equal and opposite reaction results in the aircraft moving forward. And finally, we reach our last force, drag. Drag is the force opposing thrust which limits the forward speed of an aircraft. There are two types of drag, parasite and induced drag. Parasite drag is a direct result of the air resistance as the airplane flies through the air. There are three types of parasite drag: form drag, interference drag, and skin friction drag. Form drag results from the turbulence created as the air tries to flow around the aircraft. Aircraft with larger cross-sections will have higher drag than thinner, more streamlined designs. Other items, like the landing gear and the antennas on the aircraft, will also create form drag. Interference drag occurs in locations over the aircraft where different surfaces meet. For example, where the wings attach to the fuselage. Placing two objects close together will create up to 200% more drag than if each object were separate. To minimize this, manufacturers will place smaller, angled pieces at these locations. Skin friction drag is caused by the rough imperfections of an airplane's surface. A good example of this are the rivets located on the airplane's skin. These bumps disrupt the airflow from otherwise flowing smoothly along the surface. Keeping the surfaces clean and waxed, while also utilizing flush-mounted rivets, will minimize the production of skin friction. The amount of parasite drag varies with the speed of the aircraft. As the airplane's speed increases, the amount of parasite drag will also increase. In fact, the amount of parasite drag you experience is directly proportional to the square of the airspeed. For example, an aircraft traveling at 120 knots will experience 4 times as much parasite drag as the same plane going 60 knots at the same altitude. The other kind of drag is lift-induced drag, more commonly called induced drag. While the wing is creating lift, behind the wing is a downwash of air. At the same time, the airflow around the wingtips are creating vortices that spiral from below the wing to above the wing. As these vortices wrap around the wing, they actually change the downwash angle of the air flowing over the wing. This, in effect, tilts the direction of the lift created backwards. This shift from completely vertical lift to slightly aft is due to induced drag. Induced drag is higher at slower airspeeds and decreases as we increase speed. This is because induced drag is worse when the airplane is flying at a high angle of attack, such as when we are flying slowly. One way that a pilot can experience reduced induced drag is by flying in ground effect. When flying within a wingspan of the ground itself changes the downwash of the air flowing over the wings. This shifts the lift vector forward and reduces the amount of induced drag. Pilots can take advantage of ground effect when performing a soft field takeoff. This lets the airplane lift off the ground before the regular liftoff speed. However, they'll need to hover over the ground for a few seconds to increase their speed before they can continue to climb out. If we take both induced and parasite drag, plot them on a graph, and add them together, we get a new curve representing total drag. The lowest point on the total drag curve shows the airspeed at which we make the most amount of lift and the least amount of drag. This value is called L/D max, or as pilots know it, our best glide speed. Pilots should be familiar with this number because in the unlikely event of an engine failure, this is the speed at which they'll want to glide down to the ground. In a no-wind condition, this speed will give the pilot the best glide ratio, meaning that they'll be able to stay aloft the longest to maneuver to their intended field for emergency landing. Note on the left side of the total drag curve, the slower you fly, the more drag you create. In this region of airspeed, sometimes called the backside of the power curve, the pilot will actually have to add more and more thrust to counter the high amounts of drag being created. In fact, if they want to accelerate out of this range of airspeed, they will have to add an excessive amount of power, maybe even full power. One other thing to keep in mind at slow airspeeds is that there is much less airflow traveling over the flight control surfaces. As such, any input you make on the flight controls will not have the fast response one would be used to. The flight controls will feel mushy. and may require large inputs before any real response is felt.